Hess's law. Enthalpy is a state function. This means that any change in enthalpy that occurs is independent of the pathway that is taken to achieve that change in enthalpy. The process can be explained as a series of steps then. If I have a series of steps that combine together to achieve the overall change, such as a reaction being equal to process A plus process B plus process C. Hess's law then, or the law of heat of summation, states that the enthalpy change for the reaction would be the same for a single step process as it would be for a multiple step process. So both things ending at the same point and beginning at the same point, it does not matter which route one takes to get from point A to point B. All that matters is the location at point A and point B, or the difference in energy from point A to point B. This is called Hess's law. And Hess's law states then that the sum of the enthalpy of reaction for each step of the process is equal to the overall change in the enthalpy of reaction. So if I look at the enthalpy of the reaction, then that is equal to the enthalpy change of process A plus the enthalpy change of process B plus the enthalpy change of process C. The formation of carbon monoxide from graphite and oxygen is an example of this. If the overall reaction takes graphite and combines it with oxygen gas to produce carbon monoxide, what is the overall enthalpy of reaction for this, or heat of reaction? We can use Hess's law to combine known reactions to find an unknown in this case. There are 3 different rules that we need to apply in order to use this kind of process, and they relate to aspects of the enthalpy change. If I have a different number of mole reactions overall, where the entire process as written is 1 mole reaction, if I change the number of mole reactions, then I have to change the resulting enthalpy of reaction by the same amount. For example, if I have 2 mole reactions worth of a substance, then the enthalpy change that occurs is 2 times the enthalpy change of a single mole reaction. If I reverse the reaction, that reverses the sign of the enthalpy change. Overall, additive steps mean that the sum of those additive steps is equal to the overall reaction. So the overall reaction is the sum of each individual step, and that is just another restatement of Hess's law. So if I have for this process known reactions such that graphite plus oxygen yields carbon dioxide with an enthalpy of reaction of negative 393.5 kilojoules per mole reaction, carbon monoxide plus 1/2 oxygen yields carbon dioxide with an enthalpy reaction of negative 283.0 kilojoules per mole reaction, I can combine these two together such that if I take the reaction as written for the first and reverse the second reaction, then the overall reaction I get, the carbon dioxide will cancel because it's equal amounts on both sides of the arrow, one on the left, one on the right. 1/2 of the oxygen on the top will cancel with the 1/2 oxygen on the right hand side. So overall we're left with carbon as graphite plus 1/2 oxygen yields carbon monoxide, which is the reaction that we were looking for. Now, if you notice, with the second reaction, because we reversed the reaction, we have to reverse the sign of the enthalpy. So it was a negative 283.0 kilojoules per mole reaction. Now that's a positive 283.0 kilojoules per mole reaction. When I add the enthalpies of reaction together, I get the overall enthalpy of reaction at negative 110.5 kilojoules per mole reaction. We can express the previous reaction graphically, as we see here. If we take carbon as graphite, reacting with oxygen, that can go directly from those elements down to carbon dioxide with an enthalpy of negative 393.5 kilojoules. We can also go from graphite and oxygen to carbon monoxide in 1/2 O2 with an enthalpy release of negative 110.5 kilojoules. From there, we can go down from carbon monoxide and the 1/2 O2 to carbon dioxide at negative 283.0 kilojoules. So the overall change then, if I move straight down from the reactants to CO2, I can get an enthalpy. I can then go up from there to reach the CO plus the 1/2 O2, which is what we did in the Hess's law process. So that the overall change in reaction is represented by the red arrow, the negative 110.5 kilojoules. The sum then of step 2 and step 3, or the first process here, negative 393.5, and negative 283, if that was reversed, would equal negative 110.5. Or we can take negative 110.5, add that to negative 283, and that gives us negative 393.5. So either way, adding the two steps together yields the third step by itself. Now, standard state is important in considering energetics. A thermodynamic standard state, or is referred to just as a standard state, is the most stable form of a substance, which is usually at 1 atmosphere of pressure and 298 Kelvin. Conventions involved in standard state are that a pure substance, as a liquid or a solid, has a standard state that is that pure liquid or solid. In a gas, the standard state is the gas at 1 atmosphere of pressure, or if that gas is in a mixture, it is a partial pressure of that gas at 1 atmosphere of pressure. For a solution, the standard state is a 1 molar concentration of that solution. We often change things at standard state. For instance, change can occur at 1 atmosphere. We indicate change that occurs at standard state with a superscript of 0. For example here, change in internal energy at 0 would be internal energy change at standard state. The standard enthalpic change, or delta H naught of the reaction, is a measure of the reactant at standard state going to the product at standard state. The reactions at standard state then are going to be the reactant as the beginning point and the product as the ending point, both measured at standard state, and then tracking temperature and pressure changes throughout the reaction to get the overall energetic changes of the reaction. Molar enthalpies of formation are the energy that is released or absorbed in the formation of 1 mole of a substance from its component elements. A standard molar enthalpy of formation, or delta HF naught, reflects the substance that is formed at standard state from elements in their standard states. This is also called the heat of formation, or the standard molar heat of formation. A negative heat of formation is exothermic, and a positive heat of formation is endothermic, like the other enthalpies which we have dealt with in the past. A 0 as a superscript, the naught sign, designates a standard state with 1 atmosphere of pressure and usually 298 Kelvin. Now, a balanced chemical equation, as we normally see them, may not reflect the enthalpy of formation at standard state. For example, this reaction of H2 as a gas plus Br2 as a liquid yielding 2HBr as a gas has an enthalpy of reaction at negative 72.8 kilojoules per mole reaction. In this case, 2 moles of HBr are formed. The molar enthalpy of formation reflects the energy to form 1 mole of a substance from its elements. So the actual formational enthalpy that we need is negative 36.4 kilojoules per mole reaction, not negative 72.8, because that is 1/2 of the enthalpy of the reaction, which would be what 1/2 of 2 moles would be. So to rewrite the equation then, 1/2 H2 as a gas plus 1/2 Br2 as a gas, as a liquid, produces HBr as a gas. This has an enthalpy of reaction of negative 36.4 kilojoules per mole reaction, and thus a heat of formation of negative 36.4 kilojoules per mole. Now this applies only to the given state, for in this instance HBr as a gas. HBr as, say, a liquid would have a different enthalpy of reaction and therefore a different heat of formation associated with it. Now Hess's law can be used with heat of formation. You can apply this to the formation of a substance. For example, if I want to form acetylene, C2H2, such that 2 graphite carbons plus H2 as a gas yields C2H2 as a gas, what is the molar enthalpy of formation? I can find it from component molar enthalpies. Carbon as graphite plus oxygen yields carbon dioxide, as we've seen before. It has a heat of reaction of negative 393.5 kilojoules per mole reaction. H2 plus 1/2 O2 yields water as a liquid. This has a molar enthalpy of reaction at negative 285.8 kilojoules per mole reaction. Acetylene plus oxygen yields 4 carbon dioxide and 2 H2O by combusting 2 acetylenes and 5 oxygens, with a molar enthalpy of reaction of negative 2598.8 kilojoules per mole reaction. We can work backwards to find the equation of interest. 2 carbon as graphite plus 2 O2 yields 2 CO2 as a gas. This is twice the graphite equation above, so it's twice the molar enthalpy that was listed. H2 plus 1/2 O2 yields H2O as a liquid. This is the same as what we saw above. For the last reaction, we have to both reverse the reaction because in the reaction above, C2H2 is on the reactant side, not the product side, and because C2H2 is represented with 2 moles of C2H2 and we want to form only 1, we have to also cut the reaction in half. So we wind up with 2 CO2 plus H2O yielding C2H2 plus 5/2 oxygen. So our energetic then is a reversal of the sign and cutting the reaction in half. Now to see what we get from a balanced reaction from this, the oxygens all cancel because 5/2 oxygen is the same as 2.5. We have on the right 2.5 and on the left 2 plus 1/2 or 2.5, so they all cancel out. The 2 carbon dioxides on the right and the 2 carbon dioxides on the left cancel out. The 1 water on the right and the 1 water on the left cancels out. This leaves us with a net reaction of 2 carbon as graphite plus H2 as gas, yielding C2H2 as gas, which is the equation for which we were looking. The heat of reaction, therefore the heat of formation for this, is going to be a combination of the enthalpies above, or negative 226.6 kilojoules per mole reaction. This demonstrates the formation of 1 mole of acetylene in standard state from the elements in their standard states.